Limits and continuity. So there's a few key ideas that we need to make sure we know. One of them is the issue of differentiability. Differentiability implies that the f of x, if it's differentiable, that it's smooth and continuous. And what it also implies is that the f prime, the derivative, must be continuous. So if it's smooth and continuous, the derivative is defined for all values, and that means that the f prime graph must be continuous. If we can draw a function through x equals a without lifting our pencil, it is continuous. Okay, so that is a visual check would be is if we can just draw, but if we have to at one point lift our pencil and then start drawing again, that is when we have a discontinuity. Okay, so that is a good check. So if we can draw through that point without lifting our pencil, it's continuous. Now there is a formal definition for this. That issue of continuity is the fact that if the left-hand limit and the right-hand limit must be equivalent. Okay, so it must have a two-sided limit. And not only that, the second part of that is that limit must also be the value at that point. So we actually not only have to have a limit at that point, because it could be a hole, we have to fill that hole with the actual coordinate. L'Hopital's rule is something that we're going to use for limits. And in order to be able to use L'Hopital's, we have to have the condition. And for AP Calculus, we have to state the condition. We have to state the condition of 0 over 0 or infinity over infinity, which is the indeterminate form. So we'll have to do lots of limits. Some of these limits can be done algebraically with L'Hopital's. We can do some of these limits graphically by just looking at the graph and looking at what's happening on the graph as left-hand limits, right-hand limits, or two-sided limits. We'll have to apply some of our strong versus weak arguments for limits at infinity. Those don't work for local limits, but limits at infinity, we can use our strong over weak arguments. Doing our examples here, so looking at example 1, we have a piecewise function. And so for piecewise functions, we have to check for continuity at the point where it transitions from one part of the graph to the other part of the graph. So here we have a left part of the graph from 0 to 2 is defined by log x. And then we have the right part of the graph, which is defined from 2 to the right as x squared log 2. And we want to see what's happening when the limit as a two-sided limit goes to f of x. So does it go to the same point from the left and right side? So what we can do is we can test these limits. So from the left side, we're going to do this. So limit as x approaches 2 from the left side or the negative side, log x is equal to log 2. Okay, and then we check what's happening on the right-hand side. So limit as x approaches 2 from the right-hand side of x squared log 2, that becomes 4 log 2. So we know that the left-hand limit of f of x is not equal to the right-hand limit of f of x. So if that's the case, we say that the limit does not exist. Okay, so the limit does not exist in this case because the left-hand limit and right-hand limits are not the same. Example 2, we have f of x being a piecewise function, and the question is asking for the continuity at x equals e, where the transitions from one side, the left side, to the right side. So looking at the left side, which is defined by 2 log x, we can check to see what the limit is from the right-hand side. Okay, so from the left-hand side. So we're going to check the limit as x approaches e from the left side of 2 log x. And so that's going to be 2 log e. Log e is 1, so that's going to be equal to 2. And then we could test for the right-hand side, which is defined by that expression. So we check the limit as x approaches e from the positive side of 2 over e to the x minus e. When we plug e in, we get e to the 0 in the denominator, which is 1. So that's equal to 2. Okay, so, and we know that it's defined, f of 2 is defined by the upper function. F of 2 is also equal to 2. So the limit as f of x goes to e is equal to 2. And because it satisfies the second condition, okay, so first condition is the two-sided limit being equal to 2. And the second condition is that the value at e is equal to 2. I made a mistake here. We have to write this as f of e is equal to 2. So that's our second condition. Okay, we know that it is continuous at x equals e. So we can say it's continuous. Okay, the second part of this, does f prime exist at x equals e? To do this, we need to test the left side and right side derivatives and see that the left side slope is equal to the right side slope. So we're going to differentiate this, and we need to differentiate the left side of this. This just becomes 2 over x, and that's for 0 to e. And I'm just going to do that for now. And then the right side limit is going to be, this is going to be 2e to the negative x plus e. And then because that is a negative, we need to multiply by an extra negative there, okay, for chain rule. So all I've done is put the e function in the numerator as negative x plus e. The derivative of the e function is itself. And then because of that negative exponent, we have to apply that negative for chain rule. And then we can test the limit. So the limit as x approaches e from the negative side of f prime of x, okay, that's going to be equal to 2 over e. And the limit as x approaches e from the positive side, well, that's going to be equal to f prime of x. When I plug e into that expression, I get negative e plus e is 0. So that's equal to negative 2 times 1, or negative 2. So the derivative slope on the left side, left-hand slope, is not equal to the right-hand slope. We know that the derivative does not exist at e. So f prime does not exist at e. So I'm just going to write it like this. F prime at e does not exist. Okay, so it's going to be like a kink at that point.